Hello learners, welcome to the session. Today we are going to discuss the chemical properties of haloalkanes and haloarenes. In the previous session we have completed till the physical properties of these halogen containing compounds. Now it's all about the chemical properties, which kind of a little bit difficult to understand, but if you understood it very clearly it will be very simple for you. First of all, let us start with the case with haloalkanes. So mainly we need to study three reactions related with haloalkanes. Let us check what are they. Here comes the reactions of haloalkanes can be divided into the following categories. Three categories are there. What are they? Let us check it one by one. First of all, it is nucleophilic substitution reaction. The first reaction that we are going to discuss is nucleophilic substitution, and today in the session we are going to discuss this particular reaction of haloalkanes. And the second type is elimination reaction, and the third type is reaction with metals. These are the three reactions of haloalkanes that we need to discuss, and today we are going to start with the nucleophilic substitution. Very important portion of this chapter. Most of the questions for the NEET examinations will comes from this particular topic. Okay, so nucleophilic substitution. Okay, what do you mean by nucleophilic substitution? We are going to discuss each and everything related with this nucleophilic substitution. Okay, we are going to start with what is a nucleophile. Okay, so here the reaction in which a nucleophile replaces already existing nucleophile in a molecule is called a nucleophilic substitution reaction. What is a nucleophilic substitution reaction? Here, a nucleophilic substitution reaction is a reaction in which there will be a nucleophile which replaces an already existing nucleophile in a molecule. Okay, and the reaction can be called as nucleophilic substitution reactions. Okay, let us discuss what is a nucleophile. Okay, you are kind of having a doubt, right? What is a nucleophile? Let us solve your doubt or query. Here, nucleophile means, the word phile means loving. Okay, and nucleo means nucleus. So the species that are loving the nucleus. Nucleus is having a positive charge. Why these species are loving the positively charged species? Why is it so? Because they have a lot of negative charge. Okay, they are having a lot of negative charge. That is the reason why they are loving the nucleophile. They are loving the nucleus. Therefore, the name nucleophile. So we can call nucleus loving, or they have lone pair or pi electron cloud with them. They are having a lot of negative charge with them. They are having either a lone pair or a pi electron cloud. Also, they are electron rich in nature. That is what nucleophiles are. Okay, is this clear? Nucleophiles means nucleus loving. They have lone pair or a pi electron cloud, and they are electron rich in nature. Right, then these nucleophiles are of different types. Here the negatively charged nucleophiles, examples are Cl minus, OH minus, hydroxide, NH2 minus, HSO4 minus. All these are examples of negatively charged nucleophiles. Then some of the nucleophiles containing lone pairs, or we can call them as the neutral nucleophiles. These are some of the neutral nucleophiles. They are not having they negative charge. They are having some lone pair of electrons with them. Example, water. Oxygen is having the lone pair. Ammonia, nitrogen contains the lone pair. ROH, in alcohols, oxygen contains the lone pair. In amines or NH2, nitrogen contains the lone pair. So these are examples of neutral nucleophiles or lone pair containing nucleophiles. Then the next one, those which contain the pi electron cloud. Okay, when there is a overlap between the p orbitals, there occurs these pi electron cloud. So these nucleophiles, examples is ethene, CH2 double bond CH2, ethyne, CH triple bond CH. Okay, for the formation of pi bond, the p orbital sidewise overlap of the p orbitals takes place, and there will be pi electron cloud formation, and they can also act as a nucleophile because of this pi electron cloud. Examples are ethene, ethyne are some of the examples. So nucleus means nucleus loving, or they are having lone pair or pi electron cloud. They are electron rich in nature. Three types of nucleophiles: negatively charged, neutral, and those which contain pi electron cloud. Is this clear to you? So we have studied the first thing related with nucleophilic substitution reaction, that is about a nucleophile. What is a nucleophile? This is what we have explained. Okay, I hope it is very clear to you. Now we are going to discuss another kind of nucleophile. We can call it as ambident nucleophiles. Ambident, what is it? Have you ever heard the name ambident? You have heard about ambidentate ligands, right? Those ligands which can link to the metal through more than one donor atom, we can call it as ambidentate ligand. Thiocyanate is an example of a ambidentate ligand. Right here, ambident nucleophile, the meaning is the same here. The groups like cyanides and nitrates possess two nucleophilic centers. They are having two nucleophilic centers. That is the reason why they are known as ambident nucleophiles. What are they known as? They are known as ambident nucleophiles. Example, here you can see, if we are taking cyanide, C triple bond N, and here C with a lone pair of electron and double bond N. Here in the first case, the linking takes or the linkage is taking place through carbon atom, and we can call as alkyl cyanides. In the second case, the linkage can take place through nitrogen atom, and we can call it as isocyanates. Okay, so ambident nucleophiles meanings the groups like cyanates and nitrates possesses two nucleophilic centers. Okay, another one is NO2. The linkage can happen through oxygen atom, which results in alkyl nitrites, and linking can also occur through nitrogen atom, which is nitroalkanes. So these are some of the ambident nucleophiles. Okay, so I hope everything about nucleophile is very clear to you. Okay, now moving on to the general nucleophilic substitution reaction for haloalkanes. Okay, how does the nucleophilic substitution reaction takes place? So nucleophile means the nucleus loving species. They can donate electron pairs to others, right? Now what happens here? If we are taking a haloalkane here, okay, here it is a very simple haloalkane, CH3X. Okay, then there comes a nucleophile. Okay, there comes an what? Nucleus loving species. The species containing more negative charge. That is what nucleophile. What happens here? The resultant will be, here is the resultant. Okay, as you can see, what happens? By removing the halogen. Okay, nucleophile substitutes the position for halogen by removing the halogen there, and there forms a new compound. Right? So this is generally how the nucleophilic substitution reaction takes place for haloalkanes. Okay, is this clear? And the nucleophilicity. What do you mean by nucleophilicity? Nucleophilicity is the power of the nucleophile to react. Please note down. It is the power of the nucleophile to react. Okay. Power of the nucleophile to react is what we can call as nucleophilicity. Then nucleophilicity is directly proportional to electron density. That means if the nucleate is more electron rich, okay, more electron rich means okay, the nucleophile is highly reactive in nature. It is having a greater nucleophilicity. Okay, so more the negative charge, more electron rich the nucleophile is, that much reactive the nucleophile is. Okay, then nucleophilicity is directly proportional to reactivity. More the reactive species, of course, the nucleophile has also a greater reactive what? Type. Okay, so nucleophilicity is directly proportional to reactivity too, and it is inversely proportional to stability. As we know, if someone is more stable, do they take part in any of the reaction? No, right? Because stable means they like to remain stable without participating in any of the reaction. So stability, the power of the nucleophile to react is less. Okay, less reactions will take place in the case of more stability. So more stability, the nucleophilicity is less, or we can say nucleophilicity is inversely proportional to stability. Is this clear? So nucleophilicity is directly proportional to electron density and reactivity, whereas it is inversely proportional to stability. Is this clear? So this is how generally the nucleophilic substitution reaction takes place for haloalkanes. Now we are going to check the two different types of nucleophilic substitution reaction. Please note down, there are two types of nucleophilic substitution reactions. The first type is SN2 reaction, substitution nucleophilic bimolecular reaction, and substitution nucleophilic unimolecular reaction. Two types of nucleophilic substitution reactions are there, SN2 reaction and SN1 reaction. Is this clear? Okay. In the session, we are going to discuss in detail about this SN2 reaction. Okay, we are going to discuss in detail about the SN2 reaction. Here comes the substitution nucleophilic bimolecular or SN2 reaction. What is this? Okay, so I think in the beginning of this chapter we have discussed a very little about this substitution nucleophilic bimolecular reaction. Do you remember? Okay, no issues. I will explain it once again here. These reactions follow second order kinetics. It is following the second order kinetic. That means the rate of a reaction depends upon substrate as well as the attacking nucleophile. Okay, the rate of the reaction, second order kinetics means the rate of a reaction depends on the substrate as well as the attacking nucleophile. We can write rate is directly proportional to the substrate and the attacking nucleophile. The rate of reaction directly proportional to substrate, concentration of substrate into attacking nucleophile. That is how we can say it is following second order kinetics. Then for this reaction, SN2 reaction, the reaction occurs in a single step. The reaction occurs in a single step. Important point. Okay, for SN2 reaction, it follows second order kinetics. The reaction proceeds in a single step. Then the reaction between CH3Cl and a hydroxide ion to give methanol and a chloride ion. The reaction, as you can see here, hydroxide is a nucleophile, OH minus is attacking the CH3Cl. Then what happens? There takes place the formation of an intermediate, right, which transforms into the product by eliminating the halogen, and there comes the nucleophile attached with the alkyl halide. Okay, so this is how generally the SN2 reactions takes place. It takes place through a single step by an intermediate formation. Let us discuss a mechanism for this substitution nucleophilic bimolecular reaction in detail. Okay, we are going to discuss the mechanism of SN2 reaction. The nucleophile approaches the alkyl halide molecule from the side opposite to that of the departing group Cl minus. Okay, so here let me show you. This is our alkyl halide, and as you can see, this is the departing group. Halogen is the departing group or the leaving group. On this reaction, when this reaction takes place, when nucleophilic substitution reaction takes place, generally we can say the halogen moves away and the nucleophile is coming. So halogen here is the leaving group or the departing group. So the nucleophile approaches this alkyl halide, okay, from the side opposite to that of the departing groups here. Okay, so here you can see Cl is in the right position. Right? Cl is present in the right position. Therefore, the nucleophile approach our alkyl halide through left. Okay. Here, this is what meant by the sentence. The nucleophile approaches the alkyl halide molecule from the side opposite to that of the departing group Cl. Here, Cl is present on the right side. Then, of course, the nucleophile will approach the alkyl halide from the left side. Okay, from the left side if the leaving group is on the right side. Okay, so as you can see here, the nucleophile is approaching our alkyl halide. Okay, you can see here. Then the nucleophile approaches towards the alkyl halide and you can see a shift in the bond of these hydrogen atoms. Right, now here comes the nucleophile more closer towards the alkyl halide. Okay, what happens here? Now there take place the formation of an intermediate. Okay, so here the incoming group will start to form a bond with the carbon bearing the halogen. That means the nucleophile is the incoming group here, which will form a bond with the carbon bearing a halogen. At the same time, the leaving group Cl- will start to take the grip of the bonding electron pair towards it. Okay. The nucleophile, as you can see here, let me show you. Okay, it start approaching the alkyl halide through the opposite side, right? And it approaches, comes near and forms a bond with the carbon atom. Okay, it forms a bond with the carbon atom, which you can see here. And what happens here? The chlorine group, the halogen is the leaving group. Okay. Now, it will start to take the grip of the bonding electron pair towards it. Okay, this bond, the bond between the carbon and the chlorine, okay, it starts to fade. As you can see, the bond shift, the electron pairs is taken by the chlorine atom, which is the leaving group here. So, this is what we can call as the pentavalent transition state. Here you can see carbon is having 5 bonds around it. Weak bond with a nucleophile, weak bond with a chlorine and 3 hydrogen atom, right? Here we can call it as the pentavalent transition state. What is it? It is the pentavalent transition state. After the formation of this pentavalent transition state, the leaving group, that is a halogen, is removed from there. Okay, the halogen, the bond, the electron pairs is taken by the halogen, that is by chlorine, and the bond between the carbon and chlorine breaks, and here now the pentavalent carbon is now become tetravalent, the correct valency. Okay, and the leaving group leaves the alkyl halide. Okay, so the leaving group leaves the group from here. Okay, it will leave. As you can see, say a bye to the halogen, it is leaving. So this is how the reaction mechanism of substitution nucleophilic bimolecular reaction takes place, and here there takes place the inversion of configuration. There takes place the inversion of configuration in substitution nucleophilic bimolecular reaction. Okay, our alkyl halide was like this: Cl, H, H, H. After the formation or after undergoing the substitution nucleophilic substitution reaction, here there take place an inversion in the configuration. As you can see, the 3 hydrogen atoms at first they are on the left side, and after the formation of the product, these hydrogen atoms are on the right side. There takes place the inversion of configuration for this particular group. So when a compound undergoing what? Substitution nucleophilic bimolecular reaction, there takes place a formation of a transition state. It takes place in a single step, and also there occurs the inversion of configuration. Is this clear to you? Okay. Now here, as you can see, the SN2 key points. What are the things that you need to understand from this particular nucleophilic substitution by molecular reaction? So first of all, it is a second order reaction. That means the rate depends on the substrate and the attacking molecule. Then as the reaction proceeds, there takes place the formation of a pentavalent transition state. Okay, and the nucleophile approaches the alkyl halide through the opposite, so through the side opposite to the halogen is attached. Okay, then there takes place after the product formation. Here you can see this was our reactant. Okay, and here this is the product. There takes place the inversion of configuration in SN2 reactions, right? And it is a single step reaction. The order of reactivity is inversely proportional to steric hindrance. If the steric hindrance increases, the order of reactivity decreases. More the number of methyl or ethyl group present, it will be having less reactivity. Therefore, the order of reactivity is primary alkyl halide is more reactive when compared with the secondary, which is more reactive when compared with tertiary. So, as the hindrance increases, the order of reactivity decreases. Therefore, primary alkyl halides, okay, they are having the greater reactivity in the case of substitution by molecular nucleophilic substitution by molecular reactions or SN2 reaction. So these are the key points of SN2 reactions that you need to keep in mind. It is a second order reaction. It takes place in a single step. There takes place the formation of a pentavalent transition state in this case, and also inversion of configuration takes place. The order of reactivity is inversely proportional to steric hindrance. Primary alkyl halide is having greater reactivity than secondary, which is having greater than the tertiary. Okay, is this clear to you? I hope it is very clear to you. So it is all about today's session. So we have discussed about the chemical properties of haloalkanes, and we have started the nucleophilic substitution reactions. They are of two types, SN2 reactions and SN1 reaction. Today in the session we have completed the SN2 reaction, substitution nucleophilic bimolecular reaction. I hope it is very clear to you, because this is one of the most important thing that you want to study. Okay, so we will meet in the next session with substitution nucleophilic unimolecular reaction. So we will meet in the next session with the stereochemistry of this SN2 reaction. Until then, happy learning. Thank you.